Hello everyone, my name is Hritik Saini and today I am going to present on the topic the inverse Laplace transform. Let us first see what is Laplace transform. Laplace transform is very similar to Fourier series. In Fourier series we have complex function of a real variable. Mm, Most of the time it is frequency, and whereas in Laplace transform we have complex function of a complex variable. We can calculate Laplace transform using integration 0 to infinity ft e to power minus st dt, where s is sigma plus iota omega, where sigma and omega are real variable. uh, Laplace transform can be used to solve differential equations, and it is also extremely used in mechanical and electrical engineering. Basically, Laplace transform is used to reduce a differential equation into an algebraical equation. The introduction of Laplace inverse Laplace transform. We have in mathematics the inverse Laplace transform function fs is the piecewise continuous and exponentially restricted real function ft, which has the property Laplace transform of fs Laplace transform fts is equal to fs, where L denote the Laplace transform. It can be proven that if the function fs has the inverse Laplace transform ft, then ft is uniquely determined. So this is the introduction, and then how we can calculate the Laplace transform. To find the inverse Laplace transform, we use transform pairs along with partial fraction expansion. Fs can be written as Fs is equal to Ps by Qs, where Ps and Qs are polynomials in the Laplace variable s. We have assumed that order of Qs is greater than or equal to Ps. In order to be in proper form, if Fs is not in proper form, we have used log division and divide Qs into Ps until we get the remaining ratio of polynomial that is in proper form. Then we have to calculate Laplace inverse Laplace transform. We have three cases which we consider in doing the partial fraction expansion. We have case 1, in which we have non-repeated simple roots, so we use fs is equal to k1 upon s plus p1, and then until kn upon s plus p. Then we have second case in which we have complex poles, uh, in which we use this equation fs is equal to ps by qs s plus some complex function alpha minus j beta s plus till 2, and then using partial fraction. And in case 3 we has fs has repeated poles, so we will use this type of partial fraction expansion to solve this type of equations. We will consider all the cases in detail in coming. Here uh, we have case 1. We have taken an example in which we have fs is equal to 4 plus s plus 2 s plus 1 s plus 4. So we apply partial expansion to simplify this, and finding a1 a2 a3, we have a1 4 by 27, a2 4 by 9, and a3 minus. Then we have ft is equal to this. Then we integrate it. This is a simple integration of exponential of t. We can get the final ft, the inverse Laplace transform f in time domain. Then we have second case, which is complex root, in which we use this type of partial fraction expansion. We will find k1, where s using s is equal to minus alpha minus j beta. Then k2 k1 is equal to k1 of magnitude of k1 e to power j theta. Therefore we can find inverse Laplace transform is equal to this, basically 2 k1 e to power minus alpha t cos beta t plus theta. Then we will have the last repeated roots, in which we have repeated roots. We find the coefficient of the term as follows. We find k1r minus 1, k1r minus 2 till 2 kj. Now let's talk about convolution integral. Consider with the following situation where xt is the input of the system and st is the impulse response of the system and yt is the output of the system. Now we will look at how the above is related in the time domain and in the Laplace transform. Let's see. In time domain, we can add the following: yt is equal to xt into ht convolution st. We have t is equal to 0, so like 0 to t is equal to t, xt, t minus tau, h, tau, d tau. Tau is equal to 0 to tau is equal to t, h, t minus tau, xt, tau, d tau. This is basically convolutional integral. In the case xt and ht are said to be convolute, and the integral on the right is called the convolutional integral. It can be shown that Laplace transform of xt convolution ht is equal to capital Ys is equal to capital Xs capital Hs, where we have this diagram and we have capital Hs of e to power minus 4t is 1 upon s plus 4. Now from this diagram we have capital Xs is simply Laplace transform of xt. Similarly, capital Ys is Laplace transform yt and Hs is Laplace transform st, where ht is called a simple system impulse response of the following reason. We have capital Ys is equal to x, capital Xs, Hs. Now, if the input xt is a unit impulse del t, then the Lxt is equal to capital Xs is equal to 1. Since xt is an impulse, we say that yt is an impulse response. From equation, if capital X is equal to 1, then ys is equal to hs. Since Laplace inverse transform of ys is equal to yt impulse response equal to Laplace transform of hs is equal to ht. So we have ht, that is called system impulse response. So the inverse Laplace transform of hs is the system impulse response. So we can use the inverse Laplace transform to find the system impulse response if needed by simply using hs. So about this circuit problem, we can get these equations using the basic electrical equations. We get RC dvt by dt plus vc is equal to 0, then dividing this, and then finally we get dvt dvct upon dt plus 5 vct is equal to 0. Now we can take the Laplace transform around the initial condition vc, and then we can get this equation s vcs minus 4 plus 5 vcs is equal to 0. Then we get capital vcs is equal to 4 upon s plus 5. Now we can take the inverse Laplace transform of vcs. We get again vc in time domain. We get 4 e to power minus 5t ut. So this is all about the inverse Laplace transform, and thank you.